Okay, so in this tutorial we are going to cover 15 questions. Okay, so we in the week six, I think we started with the root locus problems, and in the week 7 also it was extended in the lectures. Okay, so in week 7 what we have studied is different cases when we have k as non-negative number, that is k is negative, and also what will happen if we have the positive feedback with positive as well as negative k. Okay, so how to build the root locus in these two cases. So we have only two sets where will be following k is greater than 0, k is less than 0. Okay, so let me just go through the notes. So what we have studied in the week 7. Okay, so I'll just discuss what are the steps for the root locus again. Okay, so because in this tutorial also we are going to cover questions on root locus. Okay, so the step 1 is locate the open loop. So you will be given with the open loop transfer function. Okay, so gs you will be given with an hs. Okay, so this is open loop transfer function, where based on in today's tutorial especially we'll see what will happen if hs is +1 and -1. So +1 denotes it's a negative feedback and -1 is the positive feedback, right? So we'll be doing questions specially for the negative feedback, positive feedback. Okay, so step 1 is locate the open loop poles and open loop zeros. Okay, so it's very clear step. And second question is locate the part of the real axis that lie on the root locus. Okay, so that we have seen. And the third one is we will be plotting the assumed roots. Okay, so we'll see how many root locus or root loci will be going to the infinity based on number of zeros and poles, and we'll be calculating the angle that these assumed roots will be making, and also the point of intersection of these assumed roots. Okay, and again the other one step 4 is breakaway point and breaking point. So if we have the condition as shown here, so we'll be having breakaway points or breaking points. So breakaway point is for the if we have two poles on the real axis, and if the root locus is breaking from real axis to the complex plane, okay, then we say it's a breakaway point. And when the root locus is coming from complex plane to the real axis, or the real axis, then we call that point as breaking points. So what is special about this breakaway point and breaking point is we'll be having multiple roots for the same value of k, right? So and based on that we'll be calculating the value of k. Okay, so this is the condition. So I'll be using especially this condition if we want to. Let me just highlight this. Okay, so this condition. Okay, so I will be putting PCL equal to 1 plus k into as by bs equal to, so I'll be differentiating it and calculating the value of s. And if you get the value of s, then we'll see whether that value of s should be lying on the negative axis. It depends on value of k, right? It can also lie on the positive real axis also. So it should lie on the positive or negative real axis. Okay, and correspondingly we will be having the value of k that you'll see. Okay, so this is the procedure of calculating the k. And fifth step was how to calculate the angle of departure and angle of arrival. Okay, so the angle of departure is for the poles, open loop poles. Okay, so at what angle it will depart. Okay, similarly the correspondingly for the poles we will have angle of arrival. So for poles the value of k is equal to 0. Okay, so that's why the root locus starts from k, right? So that's why it is called angle of departure, right? And for the and for if you see what are the open loop zeros, where the root locus will come. Okay, it will be like arriving from some point, other point. So that's why we call angle of arrival. So we have studied the formulas also. Okay, angle of departure and angle of poles. So in this week we also studied the what is crossover point, right? So what is crossover point? It is the point where the root locus cuts the imaginary axis. Very simple. So if you see this example here, okay, so the root locus can your axis any point. So in the at this point also it can cut, okay, and also it can cut at the origin also. So how to calculate that? We'll just use the characteristic equation. So this is the characteristic equation, okay. And what is happening at the imaginary axis? So the real term is equal to 0, okay. So you know S is equal to sigma plus j omega, okay. But at real axis what is happening? You are making sigma equal to 0, so you are only left with S equal to j omega, okay. So we'll be finding roots of the characteristic equation at in the imaginary axis by putting S equal to j omega, okay. So you will be getting equation like this, okay. So so we know, so imaginary like the imaginary part and the real part should be equal to 0, okay. So based on value of omega we'll calculate the value of k. We'll do questions and we'll find out the what is this crossover point is, okay. But you should know what is crossover point. Definition of it: points where the root locus cuts the imaginary axis, okay. It can get anywhere including the origin, okay. So they have taken one example. I hope you have covered this, okay. So again, very interesting point was, I think, the value. Yeah. So in this problem, what happens in the case of positive feedback? So in this case, positive feedback means if you see this sign, okay. So this is positive feedback. So we are taking same GSHS, okay. So this is the same GSHS here, and k is also greater than 0. So k is your non-negative number, okay. So it's not negative, it's greater than 0. So what will happen is this will happen, okay. So if you write the closed loop transfer function equation ys by rs, you'll be getting, if you see the denominator, 1 minus gs into hs, okay. So in the previous case we are having 1 plus gshs, okay. So what is the closed loop characteristic equation? So it is equal to 1 minus gs into hs, right, which you make it equal to 0. So that is closed loop characteristic equation for the positive feedback, okay. So if you see this condition here, okay, so what is happening? You are equating the open loop transfer function equal to 1, right? So what is the implication of that? So implication, its magnitude will be equal to 1, okay. So for a closed loop pole, right? So the roots which satisfy this equation, okay. So roots that satisfy this equation will have, if you put that in GSHS, what you will get? You'll have magnitude to be 1 and the angle to be even, right? Plus minus 360 into K. So even angle. So this is opposite, right? Okay. So what are the steps? If you see here, so first step is same. So second step is so in the, if you look at the previous case, so we are considering the, so we are taking any test point. So let me take this test point. So in the previous case we are taking test point and we are seeing we were seeing at the right of that particular test point, and we are, if we are having odd number of open loop poles and zeros lying on the negative axis, then we will say root locus exists at that point, okay. But in this case it is even number of open loop poles and zeros, okay. So this is the change, okay. Now you have to consider the even number of poles and zeros, okay. So this is one change. And again, so number of assumed truths, so angle is now changed to this plus minus 360 into k and minus m, okay. So this is how we will calculate the angle of assumed truths, and point of intersection of assumed truths remains the same, that is sum of, this is sum of open loop poles, okay, minus sum of open loop zeros, okay, by n minus m, okay. So n is number of poles and m is number of zeros of open loop transfer function, okay. So that remains same, okay. So what was step 4? Step 4 was to find out the break-in or breakaway point. Okay, so now you see, so this is positive feedback, right? So now the characteristic equation is K1 minus GSHS equal to 0. Okay, so corresponding to this, you have to calculate the value of S and also value of K. Okay, so we'll see in the this today's tutorial. I think we have one question. Okay, so how will so what is the change we'll see. Okay, and again the same thing for the angle of departure and angle of arrival. Okay, so there 180 degree was there if you want to calculate the angle of departure. Okay, so just replace this with 0 degree and other things will be same. 0 degree minus sum of angles extended by poles to that particular pole minus. Okay, this was uh, just to write in short what I can say. So angles of poles. Okay, this is angles of zeros. Okay, simply what is the change? Changes here. Okay, so you are just replacing 180 with 0 degree. Okay, and again the crossover point. So now we have the characteristic equation is this. So correspondingly we'll calculate the value of omega and k. Okay, so this was one example that was taken. So they in this question for the positive feedback and for the negative feedback, so they have drawn the root locus in the same graph, so you can see what are the changes. Okay, so you can see what is negative feedback. You can see how the system is stable for particular values of k, and for the positive feedback, if you see the green locus, so you can see for any value of k the system is unstable. Okay, okay, then okay, so we have seen different values of k, right? So k can be positive and negative. Okay, so based on that we have made some tables. Okay, for the negative feedback, so this is very clear. Set 1 is when k is greater. So set 1 is what? Set of steps with the angle condition involving odd multiples of 180 degree. Okay, so if you have the negative feedback and k is greater than 0, so this first is the general case that we have already studied. Okay, and and the other case that we studied was we had positive feedback and k was greater than 2, so this was also studied. Okay, in the lecture. Okay, but similarly you can make the other case also, where for the negative feedback, if you have ka to be negative, so again you have to follow the step 2. So step 2 means you have to follow this all the condition involving even multiple of 180 degree. Okay, correspondingly if you have positive feedback and k to be less than 0, okay, you will follow the step 1. Okay, so and again in the last two lecture they have started the modeling. Okay, so this is gear transmission system. So we are just driving the transfer function between input. So input is the input torque and the output is the output angle of the output shaft. Okay, so these two shaft are coupled using this gear. Okay, so they're just using free body diagram and making the equation and just finding out the relation between the input torque and the output angle. Okay, so it's very simple. So they have neglected all the initial conditions here. So I think up to here they have studied just the modeling part. Okay, so any doubt for week 7 in theory part? Okay, so in today's tutorial I'll be covering questions on root locus, not the modeling. Okay, I think for this gear transmission the questions will be in, I think, tutorial 8. Okay, so uh, any doubt you have based on root locus for the negative feedback, positive feedback, or any value of k? Any doubt? Okay, so I'll go to the questions. Okay, so I'll read the question. So let the open loop transfer function of a negative feedback closed loop system be. So here we have negative feedback, that means HS is equal to 1. Okay, so closed loop system. So a open loop transfer function is given here where k is non-positive real valued parameter. Okay, consider the locus of corresponding closed loop poles. The region of real axis that does not lie on the root locus is. So we have to first I will write the equation for the transfer function. So this is open loop transfer function k into s plus 1 s cube plus 2s square plus 2s. Okay, so it is positive feedback and k is non-positive. So non-positive is k is less than 0, right? So k is less than 0, but what we have, other information we have is it's a positive feedback system. Sorry, it's a negative feedback. It's a negative feedback system, right? Simple. So closed loop. So if we have negative feedback system, so let me write the closed loop transfer function. So what is closed loop transfer function? Gs by 1 plus Gs into Hs. Okay. So now the characteristic equation is this. Okay. So if you equate it, you will find the roots of that characteristic equation that we call as closed loop poles. Okay. So let us first see what are the poles and zeros for this open loop transfer function. Okay. So first zeros. Okay. So if you see s plus 1 in the denominator, so you'll have only m is equal to 1, right? And where we have this 0, so let me call that set 1 at minus 1, right? And poles, so how many poles we have? Okay, if you see this equation, s cube plus 2s square plus 2s. Okay, so we have to find the poles. So you know this degree, if you see 3, right? It's a cubic equation, so we have obviously 3 number of poles. Okay, let's find where they are. 2s squares. Okay, so you know one pole will be at s equal to 0 at origin. Okay, so if you solve s square plus 2s plus 1, you'll get another 2 poles. So we just straight away write the formula for this. Okay, so we have 2 roots, so let me call this s1, this will be s2 and s3, not like this. Okay, let me just say this is s. Okay, so this is s1 is minus 1 plus j and s2 is minus 1 minus j, and let me call this third root as s3. Okay, so p1 is minus 1 plus j, this is the first pole, second pole is minus 1 minus j, and the third is at origin, right? So we have 1 0 and 3 poles. Okay, let's do the first step. Okay, by plotting in the s plane. Okay, so let me first plot the poles first. So this is p3 at 0. Okay, and p2, first p1 is here. Okay, so this is minus 1 plus j. Okay, and the other one is here, so this is conjugate pair minus j. Okay, 3 poles and 1 0, and 0 is at minus 1, so this is 0. Okay, so okay, so this is infinity. So in our question, what is asked is consider the locus of corresponding, okay, the region of real axis that does not lie on the root locus. Okay, so you have to find out, where the root locus is lying on the real axis. Okay, and just see the information. This is not a typical case. Okay, so this is, you have to focus here, k is less than 0. Okay, so we have to take those set where the angle is even multiple of 180 degree. Okay, so let me go back and this one. Okay, so if you see, we have positive feedback and k is less than 0. Sorry, negative feedback and k is less than 0. So set 2, right? So let me just rub it. So this condition we are talking in the question. Okay, so we are given with negative feedback and k is less than 0. Okay, and set 2 is even multiple of 180. Okay, okay, that means let's divide this real axis into 3 parts. Okay, so the first is minus infinity to minus 1. Okay, second region is minus 1 to 0. Okay, and the third is from 0 to infinity. Okay, so let us take test point one by one and check whether the root locus is lying in that particular region or not. Okay, so let me first take this test point here, st1. Okay, you tell me. Okay, so we have to see to the right of this test point, right? So to the right of this we have, if you see, don't consider the complex poles and zeros. In this case, we will not consider the two poles lying on the complex plane, that is minus 1 plus j and minus 1 minus j. Okay, just consider the poles and zeros on the real axis. Okay, so to the right we have one 0 and one pole, right? So total we have two, right? So what you say, whether we have root locus or not here, whether this st1 is lying on the root locus or not.
Sir, it will lie.
Okay, so we have studied a standard case where if you just remember the step 2. Okay, we have to plot the root locus on the real axis. Okay, in their standard case, what we used to see, if we have odd number of open loop poles and zeros are lying on the real axis, then we say the root locus exists. But this is not that case. Okay, so here we'll consider the even number of open loop poles and zeros, right? So we have two poles, or we'll say number of pole and zero lying on the real axis. Okay, so the number 2, so that is even, right? So we'll say the test point is lying on the root locus. Okay, so we'll say the root locus exists at that region minus infinity to minus 1. Okay, any doubt in this case? Because we are considering the case where k is less than 0. Okay, so that's why we are considering the even number. So let's go to the second region where from minus 1 to 0. Okay, so if you have, let's take a test point here is t2. Okay, so if you see to the right of that test point, so how many open loop zeros and poles are lying? So only one, right? So one is even or odd, one is odd number. Okay, so the root locus does not exist in this region. Okay, so similarly you take another test point here st3, and if you see to the right, so you'll have no open loop zeros and poles lying, right? So 0 is what? 0 is even. So we'll say the root locus exists at that point, okay? Or that st3 is the root locus. So uh, from 0 to infinity, the root locus exists, okay? So any doubt? So we have root locus in two regions, from minus infinity to minus 1, and other one is from 0 to infinity. So any doubt? So what was asked in the question? A region of real axis that does not lie on the root locus, okay? So from minus 1 to 0, root locus does not exist, okay? So the correct answer for this is minus 1 to 0. So any doubt in this question? Okay, so you have to do up to step 2, very simple, okay? So instead of odd number of poles and zeros, you have to consider even number of poles and zeros, okay, by seeing on the right hand side of test point. So any doubt? Very simple question this is. Okay, we'll go to the next question. In problem 1, which one of the following statement is true about the locus of closed loop poles? Okay, so if you see the options, it's asking about the asymptotes. Okay, so how many first is number of asymptotes? Okay, that is n minus m, right? So total number of open loop poles were 3, and we had 1 0, right, at minus 1. Okay, you see this also. So we have 3 poles and 1 0. Okay, that's why 3 minus 1 is 2. So we'll be having 2 asymptotes. Okay, so it would have, first option is straightforward wrong. Okay, so it has 2 asymptotes. It would have positive. Okay, let's find the angle also. Okay, so angle is, now the formula is changed. Okay, okay, so you know n minus m is here 2. Okay, so this is the formula now. So we'll be having 2 asymptotes, right? So let's consider k to be 0. Okay, so we'll have 0, and if you consider k to be 1, what you'll have? Plus minus 180. So let's consider plus 180. Okay, so these are the 2 asymptotes we are having. Okay, so what can you say if you have 0 degree? Okay, so asymptotes 0 degree means, okay, so it is like this. So this is the complex plane, right? So if you take one asymptotes, it will be parallel, or it will be the positive. If you say, see this 0 degree, okay, so this is positive real axis, and if you consider the plus 180 degrees, so other asymptotes will be like this. So this will be negative real axis. Okay, so entire real axis. So if you see the option, second option says it would have positive real axis as the only asymptote. No, this is wrong. Okay, so we have, it would have negative real axis. This is also wrong. So fourth option is it would have both the positive real axis and negative real axis as asymptotes, right? This is correct, right? So you say, so we'll have two asymptotes. Okay, so one asymptotes will be along positive real axis and other will be along the negative real axis. So once we plot the entire root locus, it will be more clear. Okay, so we'll be seeing how the root locus is going along this asymptotes. Okay, so this is imaginary and this is real. So any doubt in this question? Okay,
No, sir.
so k is less than 0. That's why we are following this equation, or sorry, this formula for the angle of asymptote. Okay, so this is also very simple. Okay, next question. So in problem 1, which one of the following statement is true about the locus of closed loop poles? Okay, so now if you see options, so it's asking about the breakaway and breaking point. Okay, so let's see whether break-in or breakaway point exists or not. Okay, so this was the original transfer function for open loop. Okay, and we have plotted also. So these are the poles, and we have one 0. Okay, so break-in and breakaway points. Okay, so what can you say about this? So let me ask you, then I'll go to the when we were studying about the breakaway and breaking points. So what can you say? Like if you see on the real axis, we have one pole and one 0. Okay, and we also know here in this region, so let me highlight that region. So this, in this region, the root locus will not exist. Okay, the root locus will not exist, and here root locus will exist in these 2 points. Let me just plot the region where root locus will. So in this region, root locus will exist. Okay, so let's first do the mathematics. Okay, so break in and breakaway point. So how to calculate that? So we'll take the characteristic equation. Okay, so first for that you need to find out the closed loop transfer function. Okay, so closed loop transfer function is gs 1 plus gs into hs. So since it's a negative feedback, that's why I'm putting 1 plus gs into hs. Okay, so in this case, particular case, we are concerned about the characteristic equation of the closed loop transfer function. Okay, so I'll not do full. Characteristic equation is 1 plus gs into hs equal to 0. Okay, so let me call this as polynomial ps. Okay, so how to calculate the break in and breakaway? So what we used to do is differentiate this, right? If you differentiate this and put that equal to 0 and find out the value of s. Okay, and that value of s is breakaway or breaking point. Okay, so let's do that. So first what is ps? Ps is 1 plus gs. Gs is k into s plus 1 s cube plus 2s square plus 2s. Okay, I hope this is correct. Let me just check the k into s plus 1 s cube plus 2s square plus 2s. Correct. Okay, so this is okay. So let's differentiate it. Okay, so this is 0. Okay, plus, so I'll just take out the k here. So this will be what? S cube plus 2s square plus 2s whole square. Okay, and this will be, if you differentiate s plus 1, you'll be left with 1. So s cube plus 2s square plus 2s. Okay, minus s plus 1, and if you differentiate the denominator, you'll get 3 s square plus 4s plus 2. Okay, and we have to equate this to be equal to 0. So you have to put numerator equal to 0. Okay, so you are left with 2s square plus 2s minus s plus 1, 3s square plus 4s plus 2 equal to 0. Okay, so what I am doing is, so let me just explain if you have studied the lectures. So I have done this step. Okay, so this step. So I am going, so I started with this step. Okay, so let me just mark where I started. So I started with this step. Okay, then I went to this step. Okay, okay, so now I have arrived to this step. Okay, so that's what I'm doing. Okay, so I'm just putting numerator to be equal to 0. Okay, so let's quickly solve this. Three s cube minus 4 square plus, sorry, minus 2s. Okay, minus 3s square minus 4s minus 2 equal to 0. Okay, so these are the cubic terms, so minus 2s square. Okay, so let me take what are the square terms. Okay, so which is equal to,
Sir, minus 2s cube.
okay, minus 5 square.
Sir, minus 2s cube. It's not s, sir. The first,
Once again,
the first term.
okay, cannot hear you.
The first term will be 2s cube. So it will, sir, you
Hello.
have written, sir, you have written minus 2s square.
Okay, just, I'm sorry, that is cube, correct. Oh, once again, actually, I cannot hear you. I think something is. Okay. So minus 2s cube. Okay. So you'll have 5s square. Okay. So now let's. Okay, minus 4s, I think, minus 2 equal to 0. So this is the equation, and we have to find the roots. Okay. So let me use cubic solver. So I have one root as minus 65 and s2 is minus 0.42 plus j 0.65 and s3 is minus 42 minus 0.65. Okay, so these are the three roots here, but what is originally asked here, okay, how many breakaway and break-in points it has. Okay, So only if you see on the real axis, only one point lies here, s1 equal to minus 1.65. Okay, that will be lying here. So this is minus 1 and this is 0. Okay. So how to confirm whether this point is breakaway point or not? We have to calculate the value of k. Okay, so in this case what should happen is you should get k to be less than 0, right? Then only you will confirm whether this point is breakaway or breaking point. So first let's see whether what value of k we are getting. So how to get the value of k? Okay, so use the characteristic equation. Okay, so this equation, and what is characteristic equation? This is k into s plus 1 is q plus 2s square plus 2s equal to 0. Okay, so k should be equal to minus s cube plus 2s square plus 2s by s plus 1. Okay, can you calculate the value of k? So if, what you have to put? You have to put s equal to minus 1.65. Okay, so calculate the value of k. So this will be q plus 2 into minus 1.65 square plus 2 into minus 1.65 plus 1. So can you calculate this? So I'm more concerned about the value more than the value of its sign. What should be the sign of k? So what is the value of k? Okay. So I have solved this. Okay. So you're getting minus 3.65. Just check. So if we have negative number, then only you can say it's a valid break in point. Okay. So can you confirm whether you're getting the same? Because it should come out to be this negative number. Okay. Then we can say s equal to minus 6.5 is break in point. Okay. So let's see why it is breaking point now. Okay. So you can see, so we have two poles. So these poles, if you see, lying in the complex plane, right? So what can happen is the root locus will start from here, right? From three, you'll have three root locus. So let me change the color. K equal to 0, k equal to 0, and here k equal to 0. Okay, we'll be having three root locus. Okay, and these two root locus, so I'm saying let me just draw the part of it. So these root locus will be identical. Okay, only the mirror image along real axis. Okay, so these two, so only we have these two poles which can come into the real axis. Okay, so what is that point? So that is a break-in point or breakaway point. Okay, so you see this break definition of breakaway and break-in point. Okay, so we are in this. Okay, so from the complex plane to the real axis, root locus are coming, right? So at one point they will meet. Okay, that point is break-in point. Okay, you see the situation here. Okay, so that's why I'm calling this to be break-in point. Okay, and we have also confirmed k is negative, so that's why this is break-in point. Okay, so still not calculated the angle of departure, so I don't know what angle they will make. Okay, but this we know. So what is the answer for this? So it has exactly one break-in point. Okay, so any doubt in this question? So you solve this and you just differentiate the characteristic equation and get the value of s. Okay, and for corresponding value of s, calculate the value of k, and if you're getting k to be negative, then we are assured that we'll have a break-in or breakaway point. Okay, so how we can say we have break-in points? By looking at this situation where we have two poles in the complex plane and they will be traveling to the real axis. Okay, so from from complex plane to real axis, so that point when it goes into it, converges, that point is break-in point. Okay, because that it will be coming like this. Okay, so two root locus will be coming, so that's why I'm calling this to be break-in point. Okay, okay, going to the next question. In problem 1, the angle of departure of the root locus. Okay, since we are
Sir,
having open loop poles. Okay, so that's why we are concerned about. Yes, need to. Yeah, any question?
yes, sir. Sir, if K is positive, then it will be breakaway point.
K is positive in the previous question. No, K is already given to us, right? So K is non-positive number. So K has to be negative, right? You're
Yes, sir.
saying K is positive, then what you'll have, then again this situation, what you'll have is K will be for the positive negative feedback. Okay, then you will not have this situation. Okay, let's first finish this question. Then we'll just first plot the root locus and see what is the situation here, and in the opposite situation when k is positive also, then also we can plot the root locus. Okay, we'll see.
Okay.
First let's calculate the angle of departure here. Okay, so question is angle of departure of the root locus branch from open loop pole at -1 plus j. Okay, so this is the point. So you have to calculate for this point, minus 1 plus j. Okay, so what is angle of departure for this? 0 degree minus sum of angles, okay, made by open loop poles, okay, to that point, minus plus sum of angles made by open loop zeros to that point. Okay, so let's first calculate the angles made by the open loop poles. So two poles. Okay, so if you consider this, I did consider as this as p1, this is p2 and p3. Okay, according to the question. So let's calculate the angle made by p3 at point p1. Okay, so this will be the angle, right? So I have to calculate this angle. Okay, so you know this is one and this is also one. Okay, so this angle will be 45 degree. Okay, this will be 45, and again to calculate the angle, this angle 180 minus 45, you will get 135 degree. Okay, so one angle is, so let me write 0 minus one angle is 135. Okay, so other angle is made by p2 to p1. Okay, so let me, this angle. Okay, so this angle is 90 degree, right? Very straightforward. Okay, so only we had two poles, so two angles are there. So let's calculate the angle made by zero. So only we have one zero, right? So this is 10. So what is the angle it will make? This will also make 90 degree, right? Okay, so what is the sum? Minus 135. Okay, so if you want to get positive, then 360 minus 135 you do. Okay, how much you will get? Okay, are you getting same? This is 225, so I'm writing just minus 135. So this is the angle made by this P1 pole. Okay, 225. Okay, so how the angle of departure will be? So let's make this. Okay, let me just copy this. Okay, so now we have to draw the angle of departure. So already the question is solved. Okay, so they were asking the just this root locus branch from open loop pole. Okay, angle of departure for only minus 1 plus j they were asking. Okay, so what we know about, so how to calculate for P2 angle of departure? Okay, it will be negative of that. Simple. Or you can say, okay, let me just write here. So this is angle of departure for P2. Okay, so that will be negative of, this is P1. Okay, so it will be 135 degree. Simple. So how that will look? Okay, so let me draw the angle of departures. Okay, so minus 135, so it will be looking like this. Okay, so this angle is minus 135. Okay, and correspondingly for other pole, so this is P2 and this is P1. Okay, so P2 is 135, so it will be like this. Okay, so from the real axis, if you see, this is 135. Okay, so this is the angle of departure. Okay, so let me say next question is what? Okay, so let's draw the root locus for this. Okay, so what you're seeing is root locus will be like this. So let me just draw it more clearly. Okay, so let me say this point is breaker. So change the color. Okay, so this is the root locus. Okay, so this is P1, P2. Okay, so it is going to the real axis. Okay, like this. Okay, and what is happening? So you know, one will go to here and one will go to infinity, like this. Okay, so because we know here k is equal to 0, again k is equal to 0, and here k is tending to infinity, and at this point also k is tending to infinity. Okay, and we also have one more root locus. Okay, so one more root locus is this. Okay, so it will be going to infinity. Okay, so we have seen like in which area on the real axis the root locus exists or not. Okay, so this will be the root locus. So the angle of departure, so this angle I was talking. Okay, so this is 135, this is minus 135, and this is plus 135. Okay, and this point was minus 1.65, and the value of k at this point is minus, what did we calculate, 3.65. Okay, so this will be the root locus. Okay, so here root locus is going from 0 to minus infinity. Okay, it's not going from 0 to infinity. Okay, let me say 0 to k is going to minus infinity here also. Okay, because k is negative, right? So any doubt in the root locus? So this is the root locus. Okay, so next question is simple. You can see the closed loop system of problem 1 is stable for. Okay, so just see the root locus and what can you comment on the closed loop system. Okay, let's suppose the root locus is like this. Okay, and you have to comment on the stability of the closed loop system. So what can you say? And also we know, right, k is less than 0. That's why this is plotted for k less than 0 for negative feedback. Okay, so you can see for any value of k, right, you can put any value of k. What is happening? You just focus on this part. Okay, so for any value of k you take. Okay, but so what is happening? We are having closed loop poles on the right half plane. Okay, so what can we say about the system? The system is unstable. Whatever the value of k you choose, we are always having root locus on the right half plane. Okay, so that's why we can say the system is unstable. Okay, so the correct answer would be no value of k. Okay, so how to prove it? Okay, we just take the characteristic equation, right? So what was the characteristic equation? So let's prove that. So this is the characteristic equation, right? Ks plus k. Okay, so if you write this 2s square plus okay, this is the characteristic equation. Okay, so what can you say? So what was the necessary condition? Okay, so necessary condition was all the coefficients should be of the same sign. Okay, so if you see the coefficient of sq, it's positive, coefficient of s square is also positive, and coefficient of s depends on k, right? But what about this? What about this? Because we know it is negative, right? So we know this is negative. So our necessary condition is not met. So k can be anything. Whatever the value of k, it is negative. Okay. So if you construct the Raoult's array also, okay, sq square is 0. So at the end, you put this 1, 2, this is 2 plus k and k. Okay. So here you will get 2 into 2 plus k minus k by 2, and here you will get k. Okay, but and if you see this column, okay, so you know k is negative, right? So this is negative, so you know the closed loop system will be, the closed loop will be unstable. Okay, because the roots are lying on the right half plane. And also we have confirmed by looking at the root locus also. Okay, So the answer is here, no value of k. The closed loop system of problem is 1 is stable for no value of k. Okay, so this is unstable system. So any doubt in this question? Fifth question?
No, sir.
Yes?
No, sir.
Okay. I'll go to the next question then. So sixth question is, okay. So if one has positive feedback in problem 1 with everything else remaining the same, which one of the following statement is true? So we have positive feedback. Okay. So how the characteristic equation, how the transfer function will be looking like? So this is closed loop transfer function. Okay. So closed loop transfer function is k into 1 minus gs hs. Okay, because positive feedback. Okay, and still k is non-positive. Okay, which is negative. Okay, so this is now the closed loop transfer function. Which one of the following statement is true? The locus of closed loop poles would have only one asymptote. Okay, so asymptotes, asymptote does not depend on positive or negative feedback. Okay, so number of asymptotes will be same. They will be 2, n minus 2, because in this case also what you have, n is 2, sorry, n is 3 and m is equal to 1. So number of asymptotes will be n minus m, 3 minus 1 is 2. Okay. Okay, and the second option, this is wrong. The locus of closed loop poles would have only one asymptotes. The closed loop system would be stable for all k less than 0. Okay, so this we have to check. Okay, let us draw the root locus and see. Okay, so this will be approximate. So let's see where we can do the approximation here. Okay, so we'll start from here. Okay, so let's see which case this is. Okay, so here we have positive feedback and k to be less than 0. So this case, right? Set 1. Okay, so this case. Okay, so all the steps for odd multiples of 180 will do. So let's draw it. So what we can say, the root locus will exist here, right? So second step was what? Plotting the root locus on the real axis. So we know the root locus will exist here, right? Okay, because if you take a test point here and see to the right, you'll have one pole. Okay, and for the other two regions, the root locus will not exist. Okay, and also the step 3 was break in and breakaway point. Okay, so the root locus will exist here. So if you calculate, let me see the options. The closed loop poles will be stable for k less than 0. Okay, and the other the locus of closed loop poles would have only one breakaway point. Okay, the locus of closed loop poles will partly lie in the depth. Okay, so let me just approximately draw this. Step 2 is done. So step 3 was calculating the asymptote angles, right? Okay, the 3 minus 1 2. So, okay, let me write n minus m. So this is the formula. Okay, so we need to have two asymptotes, right? So plus 90 and minus 90. Okay, so this will be the two asymptotes. Okay, so and if you want to calculate the point intersection of asymptotes, okay, so in the previous question we have not calculated it. Okay, so sum of all poles will be minus 1 plus j minus 1 minus j, okay, plus 0 minus, so 0 is only 1, that is a minus 1 by n minus m is 2. Okay, so here this will get cancelled, this is minus 2 plus 1 by 2. Okay, this is 1 minus 1 by 2, which is minus 0.5. Okay, here, so let me plot the asymptote also. Okay, so this will be asymptote at minus 0.5. Okay, and let's do the other steps. Okay, break in and breakaway points. Okay, so what can you say, like directly I can calculate mathematically, we can do all the things that we have done, like 1 plus gs into hs equal to 0. You have to differentiate and get the value of s, and then get the value of k, and we have to see whether that k is positive or negative. Okay, so basically mathematically I will not solve it, just I will write the step. So what you have to do to confirm whether the break in or breakaway point is not. So in our case here, for the positive feedback, so characteristic equation will be 1 minus gs into hs, right? This will be the case. Okay, so what you have to do, let's consider this to be ps. Okay, so you differentiate this with respect to s. Okay, and put it equal to 0. Okay, put it equal to 0 and calculate the value of s. Okay, so let me say that s is breakaway point. Okay, sa, and for that sa calculate, if you put sa here in this equation, okay, just put s a in this equation, okay, equal to 0, calculate the value of k, and if you're getting k to be negative, then we'll say breakaway or break-in point exists or not. Okay, that is the procedure. But looking at this, so what can you say, like, okay, can this two, like you have k equal to 0 here and k equal to 0 here. Okay, so what can you say, like it will, because only root locus exists between minus 1 and 0, right? It will be not existing in any of the region. Okay, so it will not have any breakaway or break-in point here. Okay, breakaway point does not exist, but I was talking about break-in point. So break-in point does not exist here. Okay, so what will happen is you'll have two asymptotes. Okay, let me first also calculate the angle of departure. Okay, you'll get k to be greater than 0 if you calculate this. So I'm saying break in point does not exist. Okay, so step 4 is angle of departure. Okay, so here the only change was this. Okay, so I'll directly write the value. So I know the value, this is 135 plus 90. Okay, This is for angle of departure for -1 plus j. Okay, and this is plus 90. So we have calculated, right? So only change is 180 degree. Okay, so this is the value. So 45 degree. So correspondingly, if you calculate angle of departure for uh, -1 minus j, you'll get minus 45. Okay, so how that will be plus 45, right? So it will be like this. This is plus 45 and minus 45. So angle of departure will be like this. This is minus 45. Okay, so actually the root locus will be going like this to infinity. Let me clearly draw along the asymptotes. So these are the asymptotes. Okay, let me just scale this and find. Okay, so consider k two poles here. Okay, so they will be going like this. So this will be one asymptote and this will be one asymptote and other asymptote will be this. Okay, so this is how the root locus of this one. Positive feedback and k less than 0 will look like. Okay, so this will be the root locus. So angle of departure also you see. So angle of departure is this. If you calculate, this will be 45 and this will be minus 45. Okay, so if you see along the asymptotes, they're going to infinity. Okay, someone was asking what will be what will be the root locus in case of opposite case. So this will be the opposite case. So that was set 2, this was set 1. Okay, so this is how the root locus will be looking like. Okay, so this is again k equal to 0, here k equal to 0, and here also k equal to 0. Okay, so what is asked, the closed loop system would be stable for all k less than 0. Correct, right? So if you see all k greater than 0, so if you see on the right hand side, so nothing is there on the right hand side. So all the closed loop poles are lying on the left hand side. Okay, so what can we say? The closed loop system would be stable for k greater less than 0. Okay, so the third option is wrong. The locus of closed loop poles would have only one breakaway point. That is also wrong. The last one is locus of closed loop poles would partly lie in. This is also wrong, right? You can see. So no part of root locus is lying on the right half plane. Okay, so this option is also wrong. Okay, so if I plot like both the root locus here, okay, let me choose. Okay, so in step 1, or sorry, in step 2, in the previous case, what was the root locus looking like? It was looking like this. Okay, and here like it's going like this. So this was the root locus. So this was set 2 and this one is set 1. Okay, so both the root locus you can see here. So any doubt here? So any doubt in this particular question? Okay, so both the root locus have plotted and shown you. So in case of this option where the feedback is positive and k is less than 0, so we can say the system can be stabilized for any value of k. Okay, so you can also okay, let us also do one more check. Okay, let's create the routes array and we'll check. Okay, so what is how to check it? So we have to check this equation, right? 1 plus gs hs equal to 0. Okay, so in the previous case also we have checked, okay, this one. So let me just copy it. Okay, this is so what was there, so you have to change. Okay, some changes was 1 plus k into s plus 1 s cube plus 2s square plus 2s, okay, equal to 0. Okay, so this is characteristic equation is, so we have minus here, right, in this case because of the positive feedback. So one change was this. So s cube plus 2s square plus 2s minus ks minus k equal to 0. Okay, this is now the characteristic equation. So if you just club all the terms together, minus k equal to 0. Okay, so necessary condition, let's, k should be negative. K is negative, that we know. Okay, necessary condition would be met. Okay, so s cube plus s square plus, okay, if we plot this, okay, this is 2 into 2 minus k plus k by 2 and this minus k. Okay, and you have to see this, and one condition we know, this one, k is less than 0. Okay, so if you consider this coefficient also, so what can you say about this coefficient? So let me write it separately. 2 into 2 minus k plus k minus 2. Okay, so it is like 4 minus 2k plus k minus 2. Okay, so this is 4 minus k by 2. Okay, so what can you say about this 4 minus k by 2? K is negative, always negative. Okay, so let me say this coefficient as b. So what can you say? K is negative. K will be always positive, right? Okay, 4 minus k is negative. You just see this equation. So let me just clearly write it here. So b will be greater than 0, right? So all the coefficient of this column will be positive, right? Minus k. So k is negative. Minus of negative number is what? Positive number. And if you see b coefficient also, 4 minus of negative number. Okay, like k can be minus 3. So 4 of minus 3 will be positive by 2. Okay, so that's why I'm saying this column will be positive always. So from the route stability criteria also we have confirmed for this particular step, set 1, the system is stable. Okay, I hope there is no doubt. Okay, 6th, quickly I have to finish. Okay, 7th. So let the open loop transfer function of a positive feedback closed loop system with this, where k is non-negative. So it is very important. Okay, so if positive feedback and k is non-negative. Okay, so consider the corresponding locus of closed loop poles. Which one of the following statement is true? So we have to do the step 2 and find out. Okay, so open loop transfer function is given s square plus 4s plus 3. Okay, and k is non-negative, that means k is positive, right? And this is positive feedback. This also information is very much important. Okay, positive feedback. So let's see the zeros first. Okay, so we have m equal to 1. Okay, so 0 is at 2. Okay, so let's take look at the poles. So poles, so s square plus 4s plus 3, so it's a degree is 2, so we'll be having 2 poles. Okay, so let's see what are the poles. So if you solve this, you'll get s plus 1 into s plus 3. Okay, so it can be factorized in this way. Okay, I hope this is correct. Okay, so one pole is at -1 and one pole will be, so let me call p1, and other pole will be at -3. Okay, so step 1 was to plot the open loop poles and zeros in the S plane. Okay, so we have minus, this is -3, this is -1. So, and we have one 0 at 2, that is +2, right? So +2 is here. So this is the open loop poles and zeros in S plane. So okay, now you have to, so you see k is greater than 0 and positive feedback. Okay, so which set you have to follow? Okay, you see we have positive feedback and k is now greater than 0. Okay, so you have to follow the step set 2. So step set 2 is what? So we'll be following all the steps for even multiple of 180 degree. Okay, so you just see this again. Okay, so now what is happening? We have positive feedback, but k is greater than 0. So this one. Okay, set 2. And set 2 is what? Same. Even multiple of 180 degree. Okay. Okay. So we'll be checking in different regions here. Again, simple. So we'll be taking few set test points here. So let me check with ST1 here. Okay, ST1. So you can see there are 3 open loop poles and zeros here. So we'll say, so let me just first demarcate the regions, -infinity to -3. Second is -3 to -1, and third is -1 2, and fourth region is 2 to infinity. Okay, so I'm checking in the region 1. So ST1 is in from -infinity to -3. So I can see there are 3 open loop poles and zeros. So that means odd, right? So odd means the root locus will not exist. Okay, so if you see from -3 to -1, so let's take one test point. So what you can see is 2 open loop poles and zeros, that is even. So the root locus will exist. And if you see the third, so let me consider this st3. So only one open loop uh, pole and zero exist on the right hand side, so we can say this is odd number, and that means root locus will not exist. And from 2 to infinity, zero number of poles and zeros lie on the right hand side. If you take this st4 test point, so we'll say that is 0 is even. Okay, so this is where the root locus will exist. So let me mark where the root locus exists. So here the root locus will exist and -1 to 2. Okay, so the region -infinity to -3 lies on the root locus. minus infinity to minus 3. Yes, no, it does. Yeah, it does not lie on the root locus. I think I have made a mistake here. Okay, so minus 3 to minus 1 and 2 to infinity. So this is where the root locus lies. Okay, so let's, first one is minus yeah, this is wrong. Okay, and minus infinity to minus 4, this is also wrong. The region minus 3 to minus 1 lies on the root locus. Correct, this is correct, right? And the region minus 1 to 2 lies on the root locus. Minus 1 to 2 does not lie on the root locus. Okay, the only correct option is third option. So you have seen from here also. So any doubt in this case? Very simple. So let's consider the odd number of open, sorry, in this case we have to consider even number of open loop poles and zeros on the right hand side of test point. Okay, I hope there is no doubt in this. Okay, let's go to the it. In problem 7, which one of the following statement is true about the locus of closed loop poles? Okay, so this question is related to asymptotes. Okay, so we all know, so already we have found out the number of poles and zeros. Okay, so number of asymptotes, so in this case is n minus m, so n is 2 and m is equal to 1. Okay, so 1, so only one asymptote it has. Okay, so it would this is all, this first option is wrong. It would have two asymptotes. Second option, it would not have any asymptote. This is also wrong. So it would have the negative real axis as the only asymptote. So let's calculate the angle. So we have to calculate the angle of asymptote to answer the, so to choose whether which option is correct out of 3 and 4. Okay, so we are following, remember, step 2. Okay, sorry, set 2. N minus 1 is 1, just 1. Okay, case, so you put just k equal to 0, you'll have 0 degree. Okay, so only one asymptote. So what can we say? We have, it would have a positive real axis as the only asymptote. Okay, very simple. Plus minus 0 is 0. Okay, only one asymptote is, we have to consider only one asymptote. So this option, you'll see, you'll finally make the root locus and you'll see why uh, this is true. Okay, from here also we can say, since the angle of asymptote is 0 degree, we'll say it has positive real axis as the only asymptote. Okay, because angle is, and if you calculate the center, so why we have to calculate the center? Okay, let's do the next question. In problem 7, the breakaway point is at, okay, breakaway point. So for the breakaway point, what we have to calculate, 1 plus GSHS equal to 0. Okay, so this is characteristic equation and calling this as Ts equal to 0, denominator. Okay, so this is 1 plus GSHS equal to 0. So what we used to do, we first calculate this equal to 0. Okay, so let me say what is gs is k into s minus 2 s square plus 4s plus 3. Okay, so this is gs is given to me, and what is given, I think positive feedback and k is greater than 0. So in case of positive feedback, we know, so ds, this is minus, okay, 1 minus gshs. Okay, so ts here is equal to 1 minus k s minus 2 s square plus 4s plus 3. Okay, so differentiate this. Okay, so 0 minus k So what you'll get in the denominator, so we're not concerned about the denominator, so we'll focus on the numerator. So what is the differentiation of s minus 2? 1. Okay, minus s minus 2, and if you differentiate the denominator, 2s plus 4. Okay. So let's take the numerator and put that equal to 0. Minus s minus 2 and 2s plus 4 will be equal to 0, and you have to find out the value of s. Okay, let's simplify this. So this is 2s square minus 4s. Okay, this is plus 4s minus plus 4 to the 8. I hope everything is correct. Simplify this. So this is minus s square. Okay, so we have pluses. Okay, so plus 11. I hope I'm making no mistake here. Please check. Okay, try to find the roots for this s1 and s2. Okay, and correspondingly you'll find the k1 and k2, and we'll see. Okay, so let me first calculate the roots. So it should. Okay, so two roots are, s1 is coming out to be minus 1.87. Okay, and the other root is 5.87. Okay, so these are the two values. Please see whether I'm making any mistake or not. Time I will just confirm. 1 minus 1, 11. Okay. Okay, so 2 points I'm getting. So k1 and k2. So here k is greater than 0. So both the values k should be coming out to be, you have to check whether k is positive or not. If it's negative, then that point is not a break-in or breakaway point. Okay, k1 and k2. So how to check k1 and k2? Okay, use this equation. Use this one. So 1 minus k is minus 2. Okay, so here k is s square plus 4s plus 3 by s minus 2. Okay, so what was the question in the breakaway point is at, okay, we'll calculate the k1 and k2. So k1 is when you put minus 1.87 in the equation, plus 3 minus 2. Okay, calculate the value. So 1.87 is also there and 5.87 is also there. So we have to see. Okay, I'll calculate the value of k. So before that, so you see options here. Okay, only two options can be correct, right? So 1.87 is there. I'm hoping that I have calculated the S1 and S2 and just assume that for each of those values, you're getting k to be greater than 0. That means they exist. The break-in and breakaway point exist. And we have to find out of these two, which is breakaway and which is break-in point. Okay, So which is break in and which is breakaway point. So let me just take the, okay, let me draw the root locus again. Get clarity here. So we have, and this was the case. Okay. Okay. So what can you say, like, so one point is lying 1.87. It's here. So this is 1.87 minus 1.87, and the other point is lying here 5.87. So let me just here. Okay, this point is 5.87. Okay, so what can you comment which will be the breakaway point and which is break-in point? Okay, so you see there are two poles, -3 and -1. Okay, and what we have seen, root locus exists between -3 and -1, you see. So there will be the root locus. Okay, so what will happen? So can you say, what can you say about this point? Minus, just comment on the point -1.87, whether it's break in or breakaway point.
So break-in point.
Break in.
Yes.
How can we break in? Because root locus will start, root locus will start from here. K is equal to 0, K will be equal to 0. Okay, as you increase the value of K, what will happen? Root locus will be like this, right? And notice this, when this happens, this is
So
break
break
in or
away.
breakaway?
So
Huh?
break away. Break
This is
away.
breakaway point, right?
Yes.
So this is breakaway. Okay. So let's, okay. So answer to this question is breakaway point is -1.87. So let's first calculate the value of K1 and K2. More clarity you'll get. Okay, I think I've calculated K1 and K2. I'll just use those values. Okay. So for S2, I was getting 0.25 and 15.75. 0.25 and 15.75 for 0.25. So I was getting these values and both were positive. Okay, so this was K1 and both are coming out to be positive. So I was certain that, so there exists break in and breakaway point. I have just to find out whether that point is break in or breakaway, right? So we have confirmed that -1.87 is break away point. So clearly you can see there exists one 0, right? So what can happen is this one, it will go from here and it will cross the imaginary axis. Okay, and it will go like this. Okay, so you see this is the root locus. Okay, and what can we say here? So two root locus are entering into the real axis. So this is break-in point, right? and one will go here and one will go to infinity. So what we have studied, so this is k tending to infinity, right? So other will also go to infinity. So and for the asymptote question, we also found out that there is only one asymptote and it is making zero angle. Okay, just see this. So only one asymptote is going to infinity, this one, right? You see, it is making zero angle, right? Okay, so any doubt in this question? So I have drawn the entire question, so it was not asked. Okay, okay. So this is the root locus. Okay, let's do this next question. In problem 7, the value of k at breakaway point. Okay, so in this particular, already we have calculated. So s1 equal to minus 187 is the breakaway point, and the value of that is at that point is k1 is 0.25.
Sir, sir,
Yes,
screen is not shared.
screen is
What
not
is it?
visible.
Yes, sir. It's not.
Can other also confirm my screen is visible or not? Can others comment like whether my screen is visible or not? Okay, because I can see it's visible. You just log out and log in. Okay, okay. So the value for k is coming out to be okay 0.25. Okay, so already we have calculated. So this is how we calculate. Okay, so this process I'll just copy it. So this is the process. Okay, I know at s equal to minus 187, that is the breakaway point, and the value at that point is value for k at that point is 0.25. Okay, and in the next problem, the break-in point, so that already I've calculated it to be 5.87. Okay, and the value of k is 15.75. Okay, so in the next question, the value of k at the break-in point is 15.7. Okay, this is already solved. Okay, okay. Next question is in problem 7, the crossover points are at. Okay, so if you see the root locus, so okay, this root locus is crossing at some these 2 points, right? So here, let me just at these 2 points, it will be crossing and going from left half plane to right half plane. Okay, and we have to find out what are those values. So these are crossover points. Okay, this value and this one. Okay, so let's calculate those values here. So calculate the value, so we'll be using this equation, 1 minus gs hs equal to 0. Okay, this is the characteristic equation, and you know the roots of characteristic equation are the closed loop poles. Okay, and at that point, you know, at the crossover point, so s equal to sigma plus j omega, so this sigma is equal to 0, so we'll be only left with s equal to j omega. So okay, first I'll write what is gshs. K is minus 2 square plus 4s plus 3 equal to 0. Okay, if you put s equal to j omega, what you will get, first square plus 4s plus 3 minus k is minus 2 equal to 0. Okay, let's take the numerator, and by putting j omega, okay, plus 3 okay, this is there. So let's just separate out the real and the imaginary parts here. So this is minus omega square, okay, plus j4 omega plus 3 minus jk omega and plus 2k. Okay, so the real parts are minus omega square plus 3 plus 2k, okay, plus j 4 omega minus k omega. Okay, so let me take omega outside. 4 minus k. Okay, so this is real part, and this is imaginary part, and both the parts should be equal to 0, right? So we know first is, like, if you see the imaginary part here, so omega equal to 0. Okay, so how the imaginary part can be 0? One case is omega can be 0, okay, and other cases k can be 4, right? So let's check the case 1 where omega is equal to 0. So imaginary part is obviously equal to 0. If you put omega equal to 0 in real part, so what you will get, 0 plus 3 plus 2k equal to 0. Okay, and if you calculate the value of k will be minus 3 by 2, which is minus 1.5. Okay, but you know k, the value of k cannot be negative, k, because it's given k is positive. Okay, so this cannot happen, so this is invalid case. Okay, so omega equal to 0 is not the crossover point. Okay, already we know, see, from the root locus we know at omega equal to 0 there is no crossover point. Okay, so that we are confirming from here, because we are getting k to be negative, that we know. Okay, let's consider the other case. So case 2 where 4 minus k term is equal to 0, so k is 4. Okay, so if I put k equal to 4 in the real part, so what I will get, what should be the value of omega? So you have to solve this equation, plus 2 into, so k is 4, right? This one. So you know omega square is, what you're getting, 11. Okay, hope everything is correct. Minus omega, yeah, 3 4 4 into 2 is 8, 8 plus 3 is 11, so omega square plus 11 omega square. So what you'll get, omega root of 11, right? Plus minus root of 11. So what can you say about this point? Root of 11 is how much? I think it's 3.32. I think so. Okay, so this can exist, right? So if you see, k can be positive, you know, k is greater than 0, right? And we also know at some point omega equal to plus minus j11, or you can say s equal to, because we know we have put s equal to j omega, right? So s plus minus j11, so these are the crossover points, right? So let me just put s equal to j omega. So we have this plus minus j root of 11, and one crossover point is plus j11, and other point is minus j11, right? So these are two crossover points. Now also, so let me copy the root locus in this question, so it will be more clear. Okay. So this is the root locus. Okay. Okay. So already we have drawn the root locus, and these 2 points are just now we have calculated it. Okay. So this is root 11, j11, and this will be minus j11. Okay. So these two are the crossover points. So this question is the crossover points are at 3.32 jn, because if you calculate root of 11 is 3.32. Okay. So this is how to calculate the value of crossover points. Okay, quickly I will. So any doubt in this question? Very simple. Already we know the root locus how it looks. Just we are calculating the value of crossover points. So what are crossover points? So and the root locus is going from one half like right from left half to right half, or from right half to left half. So in this case it's going from left half to right half. Okay. So other two questions in problem 7, the value of k at the crossover point is. So value of k. So already we have calculated, right? So this case same. So k is equal to 4, right? So answer to this is very simple. This one. So at k equal to 4, we have the crossover points. Simple. Okay. So value of k, if you put omega equal to root of 11, you will get k equal to 4. Okay. Already we have calculated. No problem. So in 15, the closed loop system of problem 7 is stable for all. So let's see, just see the root locus and we'll say, when is the system stable? So you see this is k equal to 0, k equal to 0, and at this point k is equal to 4. Okay. So as we are increasing the k, what is happening? The closed loop poles are again occurring in the right half plane. Okay. So if we limit k to be less than 4, so you can see the closed loop poles will be lying on the left half plane, right? You can see these points. Okay, as you are increasing k, what is happening? Root locus is moving from left to right. Okay, so when the system is stable when k is less than 4, right? Simply looking at this value, just look at the root locus and you can comment on the stability. So directly you can say if k is less than 4, okay, just looking at the root locus, I will just copy the root locus to that question. Okay, this is the answer. Okay, so what you want for the system to be stable, closed loop system to be stable, its poles should lie on the left half plane. Okay, it should not lie on the right half plane. So how we are ensuring it? By keeping k to be less than 4. Okay, so you know, at after the crossover points k will increase. Okay, because k is going from 0 to infinity. So what are infinity points? So this is one point, see, and this is one point. Okay, so I think this is very clear. First this question, and how to check from Raoult's stability criteria also you can check. Okay, so for that what we need is 1 minus GSHS because of positive feedback. Okay, so what is that equation? Let's, this is quickly I will do. k into s minus 2 s square plus 4s minus plus 3. Okay, if you square plus 4s plus 3 minus ks plus 2k equal to 0. Okay, okay, let me simplify this again. What you'll get is s square plus 4 minus k and 3 plus 2k, and one information we have is k is greater than 0. Okay, so this is quadratic equation, so necessary and sufficient condition are same. So that condition is your coefficient should be positive, right? Because if you see all the coefficients are positive, this is positive, right? Because k is greater than 0. Then to make this term to be greater than 0, so 4 minus k should be greater than 0. Okay, so what is happening, k should be less than 4. Same condition you'll get from this also. By looking at the root locus also, we can comment on the value of k. Okay, so this is the right answer. So any doubt on this question? 15th. Let me quickly take the doubts. So once again, tell me 1, 2 and 9. 1, 2 and 9. Okay, so ninth part. So ninth one is okay. So okay, so here you want to, okay, so in this case, so we are given with gs. Okay, gs we have, and what information, other information we have, it's a positive feedback with k greater than 0. Okay, this information we have. Okay, so the process for finding out the breakaway or breaking point remains the same. You have this ds function 1 minus gshs. Okay, just differentiate it and put it equal to 0, find the value of s. Okay, the same thing I have done here. Okay, so I got two values here, s1 and s2. Okay, and if you calculate the value of k, corresponding value of k, it is 0.25 and it is 15.7. Okay, that means k is greater than uh, sorry, k is greater than 0. That means these are break in and breakaway points that we can we are certain about this. But which point is break in or which point is breakaway point? Okay, we have to see the location of poles and zeros. Okay, so if you see the first point s1, so this is s1 and this is s2. Okay, so s1 is lying between two poles. Okay, and between minus 3 and minus 1, we are also certain that if you do the step 2, root locus exists. Okay, so root locus is existing between point 1 point minus from minus 3 to minus 1. Okay, so what will happen is if you increase the value of k from 0 to from 0, if you increase, the root locus will be going like this as I've shown here. Okay, so at one point at s equal to minus 1.87, what can happen? Okay, so only they can break away, right? So there is no point of break in. So when you have two poles lying on the real axis and the root locus exists between them, so there will be a breakaway point. Okay, if you do more questions, you will get more clarity. But between two poles, and there will be breakaway points. Okay, so this is breakaway point. Okay, and the other one is if you see here, so there exists one pole at 2. Okay, so meanwhile, what will happen? You have one asymptote, right? And one locus will go from k equal to 0 to k equal to infinity. Okay, so we have 1 0 here at 2. Okay, so one of the root locus will be going to your 0. So that's why what will happen, the root locus will emerge out from the breakaway point and they will cross the real axis, and again it will break into s2. Okay, so that's why it's breaking in from the complex plane to the real axis. That's why I'm calling this as breaking point 5.87, where k is greater than 0. And again one of the root locus will go to 2 and other will go to infinity. So that's why we had one asymptote. Okay, I hope this is very clear. Any doubt in this question? Okay, we'll go to second question. Okay. Okay, second question. Here first we have the locus of closed loop poles. Okay, this is the first question. Okay, I think there is no doubt, should be doubt in the first question. Okay, k is less than 0. Okay, and this is negative feedback. Okay, so only I'm just in different region I'm checking whether the root locus exists or not. So in this case, if you see, if you take a test point and see to the right, and if you have even number of open loop zeros and poles, then we will say the root locus exists. And if you see from minus infinity to minus 1 point, so we have taken one test point st1 here. Okay, so this is the test point, and what I can see is there are three. Okay, how many poles? There are two open loop poles and zeros. Okay, so two open loop poles and zeros means sum of that, one open loop zero and one open loop pole. Okay, so two open loop poles and zeros exist, so that's why I'm saying that is even number, so that means root locus will exist. Similarly, in case of 0 to infinity, so there will be zero number of if you take the test point st3 here. Okay, see to the right, so you'll not have any poles and zeros, so zero poles and zeros, so 0 is even number, so you'll say root locus is existing. Okay, simple. And for the problem number 2, so what you have to find, you have to find the angle of asymptotes. Simple. So since we have two angle of asymptotes, if you put k equal to 0, you'll have 0 degree, and if you put k equal to 1, you have 360 by 2. Okay, so this, if you take minus also no problem. Okay, plus minus 180 degrees the same. Okay, so only two asymptote angle of asymptotes exist. Okay, so that's why for 0 degree I have said key it's positive real axis, and for plus 180 degree I have said it's a negative real axis. And we have also seen for the final root locus, you can see. Okay, so this one and this one, so these two root locus are going to infinity along the asymptotes. So one asymptote is along the positive, so already we have, so this is along positive real axis. Okay, and this is going, this root locus is going along negative real axis. Okay, so we can confirm also from looking at the final root locus. Okay, so any doubt? Okay, already I think time is more, so okay, I think I will end the session. Okay, so I will meet you in the next session, tutorial session 8. Okay, on the next Tuesday. So thank you for attending the session. So good night. I'll end the session now.